Hey, how's it going? It's Sid Greenwood, and for my project for research phase, I did Jump Point Search Plus, which is kind of an extension of A star for a certain type of pathfinding in game AI. So here are the contents of the overview. I won't go ahead and then just list everything, but essentially we'll talk about A star a little bit, and then we'll jump into what Jump Point Search is, and slowly kind of introduce all the concepts that make it what it is. So what is A-star? A-star is an informed search algorithm, so we already know certain things and can guarantee some certain things in a grid. We can guarantee certain neighbors or costs and things like that. We then take in a series of connected nodes, which is that grid, and then we take in a start and an endpoint, and we attempt to return the least cost path back if we can find one. We utilize a weighted graph framework for that, and you utilize some sort of priority queue system, often referred to as an open set, fringe, or frontier. The general logic is as follows. You essentially loop through nodes until we reach an endpoint while comparing paths that are placed in our set, which are ones that we've determined are of a lower cost than current neighbors we are analyzing. We then loop through all those nodes, remove a lowest cost option, put it in that set for it being checked later, update neighbor weights, add them to the queue, and then continue until a goal or path is found. And then once we have finally reached the end node, we retrace a path back to where we came from. Jump Point Search Plus is a static uniform cost grid algorithm introduced in 2014. How it differs is that it implements a pre-baked system which we kind of use enhanced node pruning along with these things called jump points and wall directions while still utilizing A star at runtime. It relies upon, as talked about, a static environment and grid, so you cannot be changing walls or tiles, and of course there has to be a uniform cost according to distance traveled. And then what this achieves is that it can help pathfinding in speeds of up to 2 orders of magnitude faster than traditional A star. So for the strategy overview, traditionally A star can overwork itself with no need. If you look at the graph on the right, those are 4 different cases in which the optimal path is the same cost. So A star is going to go through and it's going to make all those calculations happen even though it doesn't need to. It's already found an optimal path. To account for half the improvement that we see in jump point search plus alone, a more selective pruning strategy is introduced. So when moving through nodes, only successors of similar nodes in a direction of a current path are taken. So if we're going diagonally from the north to the northeast node in the center, on the graph in the bottom right here, we then extend either northeast or northeast. Once a cardinal direction is taken, that is locked in. Additionally, the other half to optimization that's brought forth by Jump Point Search Plus is visualized in the graphs below. So as you could see in this comparison below, about a third of nodes are added onto the open list as compared to what A star would be doing. So for determining neighbors, we'll start with forced neighbors. Essentially, while the prune method is very effective, it has a flaw in that kind of diagonal direction and then lock cardinally logic. The fix is force neighbors. Essentially, we make flags, and where in this graph on the bottom left here, P is where we are, and when we're heading to N, depending on the direction and location of travel, there are 8 force neighbor cases. Honestly, what I found worked is I just looked at it and realized the pattern was that whenever you're heading towards the corner of a wall, that is essentially a force neighbor. Now there's jump points, and they can get categorized as a primary, straight, diagonal, or target point. Primary jump points are points that have a force neighbor, and they are used only when traveling to the point, and they only exist in cardinal directions. Again, you can kind of use some pattern recognition to realize that essentially if a node exists on the edge of a wall somewhere, it's going to have some sort of primary jump point. Straight jump points are points in a direct path to primary jump points somewhere. In the bottom left graph, they are visualized by arrows, and it's better understood when we turn it into numbers on the bottom right, so you can see essentially how many arrows were part of one jump point in the straight direction. Now you will notice if you look at this a little bit that this 3 should be a 1. There's a jump point right beneath it, it's a straight direction. Why is it not 1? Well, it's because that while it's a jump point, it's not a jump point for that direction of travel. If we were heading straight, because when we start traveling down, we are locked to only the down direction, we wouldn't care about jump points in any direction from this other than down. When I said this, I mean the node that has the 2 and the 3. Now, for diagonal jump points, we utilize the directional logic that's applied during the pruning and path selection to jump points. A diagonal direction is a direction that will reach a primary jump point or a node that is in the cardinal composite direction of a target point. Now, that doesn't make a lot of sense when you hear it, but essentially what we are saying is that normally in the very top left node here, you see this 1 in the southeast corner of the node, and that takes us one diagonal direction to a target point. However, when we look at the fourth node over, marked with the 1 and the 2, you see that it heads down to diagonally, which makes sense, but it's not to a target point. This is because if we flip the direction, which was southeast, now northwest on this target point, that north, being a composite of northwest, is a tile. So this diagonal direction will send us that way. For wall distances, this is the final step in which we have to fill in values that are not essentially already calculated. If one of the 8 directions that make up a node is not already filled up, it's marked with a distance to a wall. And then it was noted that to minimize memory usage, 0 or negative values were used for walls, and I also do think that it just kind of helps make it a little bit more readable. Alright, so now that all the logic checks out on paper, how do we actually get this baked in a grid on a machine? So a series of sweeps are done on a map, and this essentially initializes the values. First, we have to identify all primary jump points by setting a directional flag in each node. Then, for cardinal wall directions and straight jump points, which there's 4 of them, we sweep in a direction, one of those cardinal directions, and then look in the reverse of that direction, setting those straight jump points and wall directions. So for example, if we were sweeping down up, which would be northward, we would be setting all southward facing straight jump points and wall directions. And then lastly, we sweep once northward and once southward, setting the composite diagonal directions and wall directions of the backward respective directions. Essentially, a better way to understand this again would be if you're sweeping northward, you would be setting all southeast and southwest facing diagonal jump points and wall directions. As for seeing what that would look like through code, on the left is an example of the westward sweep cardinal logic, and then on the right is an example of a northward sweep for the diagonal logic. In terms of the runtime logic that we have to implement, due to all the burned in information, there's actually a lot of decisions that are removed from the process, and there isn't even necessity for the recursion that you see in traditional A-star. And this is due to the fact that we only analyze jump points and only put those on the open set, and all of those are going to be used for at least one optimal path, so we know they're valuable. We implement a static valid dir lookup table that essentially envelops our logic for the directions and their composites when searching through nodes for pruning. And wait, there's one thing missing, target jump points. We'll get to that in a second. And then finally, once all that logic is implemented, we just end with traditional A-star as we select nodes. So what are target jump points? Well, while we're searching, target jump points are points that are grid aligned to a target point on a runtime search. To find them, there are some conditions. So it's only when heading in a diagonal direction, and that direction has to be towards the goal when thinking about row or column wise. So if we start in this bottom left corner here, the column would have to be above us and the row would have to be to the right of us. The row or column distance then has to be less than or equal to the current node. So once we've exceeded the target location, thinking about this in terms of row and column space, we can't go that direction. And then this point is used because of the guarantee, essentially, that it will either be the target or have a high likelihood to be an intermediate jump point. And then here's what some of that runtime pseudocode would look like. On the left here is that valid dir lookup table. And both from the reading here and just from previous stuff I did with the mesh generation and some A-star pathfinding, I think that having certain things static for your use case essentially is really important in pathfinding and a lot of different types of kind of procedural behavior, because I definitely would classify certain types of pathfinding as a certain procedural behavior. So in terms of what all this means, in the model that demonstrated the target jump points and the end result of the pathfinding, of 10 nodes analyzed, 7 were used, meaning it's very efficient. There are some trade-offs. While fast, it's a fully static and uniform cost grid that's used, so it must be pre-processed and have 8 integers per cell. And in open environments, this method shines, but environments that are highly kind of maze-like, the performance benefit is reduced by a lot. Um, then finally, in the final conclusions of the article, there was some kind of jargon I didn't understand, but that talks about how to improve this further. So they mentioned to use a heap set algorithm for the open list. They recommended to pre-allocate all node memory along with a dirty bit for cheap initialization, and they recommended to use an octile heuristic. Here's the source for the chapter I read in the Game AI Pro book published by Steve Rabin and Fernando Silva. And are there any questions?